Let's talk into 4 parts. In the introduction part, I will talk about the idea of quantum network, and because I'm doing the theory, so I will give you some theoretical background, and then I will introduce the concept of time reverse photon, and the most important part is our motivation. So as I mentioned, I'm doing the theory, so then I will talk about our model, and then once we have the model, we can show you our numerical results. In the end, I'll conclude our work. So let's start with the introduction part. So this figure or this cartoon shows you the concept or the basic notion of the quantum network. It composed of 2 important ingredients. The first one is called the quantum dot. It is represented by the qubit box in this figure. And it can be a group of qubits or a single qubit in reality. And also these these quantum nodes are connected to each other through the so-called the quantum channel here, represented by the red arrow. And this quantum channel can be realized by using the optical fiber, waveguide, and so on. So now, for example, suppose we have a one-dimensional quantum network composed of several nodes connected to the 1D communication channel or quantum channel, and and one can perform a quantum process in each node locally. Once this process has been done, then the next step is transfer this kind of information through from node to node through this quantum channel. So you can transfer the information from left-hand side to the right-hand side. So you can realize the long-range quantum communication by using this quantum network architecture. So for more concrete example, suppose now we have a quantum network composed of 2 identical nodes. They are connected to optical fiber here, and in each node they can have optical cavity, and they have a qubit in the optical cavity. And also they can have a beam of lasers. They can locally address these atoms. And then after some process has been done, then the information must be transferred from node A to node B in terms of photon through this optical fiber. So there is a question naturally arises, like how to efficiently load photons from node to node through common channels. Okay. And there are some groups that are trying to answer this kind of questions. For example, there are some groups that are trying to use the time reverse photon or time reverse symmetry to start this kind of questions. For example, there is a group that are trying to use the single photon, the time reverse photon, interacting with the 2-level atom here, and they study the corresponding loading efficiency. And also, there's a group that propose they can use the multiple photons to increase the loading efficiency. And also, there is some group that are trying to study how to load photons into an optical cavity, or they can use or the other group they're trying to study the many-body effect or atomic cloud on the loading efficiency. Okay, so there are still some difficulties to realize quantum network by using the neutral atoms. For example, the first one is that now the incident and the radiation field usually have different spatial patterns. So this difficulty can be solved by reducing the 3D geometry to 1D geometry. This means that, for example, now we can now consider by using use the metal fiber coupled to atomic arrays, or we can just simply use the optical cavity and put all the atoms inside the cavity, interacting with this single mode of electric field. Okay, so the second thing is that now the strong line matter coupling is very hard to be achieved by using the neutral atom, because the neutral atom has a very weak or very small dipole moment. And it can be solved by using the, for example, the atomic cloud or micro example here. Can use many particles. We can use the cooperative effect collectively, you can use this collective effect to enhance this kind of line coupling, or simply we can just use an artificial atom. So in our work, we consider that we need a 1D systems and plus artificial atoms. So there is a famous one nowadays is known as the single-qubit system. So in our work, our model or wave system we consider is the single-qubit system. And so we ask a question like, can we efficiently load photons on such a single-qubit systems? Okay, this is our starting point. And before before I going to answer this kind of question, let me make a digression to talk about what kind of systems we are considering in our work. So as I mentioned, that we need a 1D system plus artificial atoms. So what kind of 1 systems we are considering? Okay, so the famous one is called the open transmission line. And we also we can learn this kind of concept from the textbook. So suppose we have the open transmission line, and then we can have input signal from the left-hand side. Suppose we can come from the left-hand side, and then we can measure the corresponding transmitted signal to the from the right-hand side. And as we know, it's kind of a transmission line supporting a traveling wave. This means that the wave can go from left to the right, and has the like the wave function. The form is like the cosine function. Now, suppose we can have a single atom here, a two-level atom here, and then after the interaction between the input signal and the qubits, we can have a reflex signal. So this means that the atom can be absorbed the photon and remit the photon to the left-hand side. So in experiment, they can measure the two signals, the reflex signal and the transmission one. Okay. And since we know that, we are trying to think about go a step further, like by asking a question like how to adjust or how to change the coupling between the transmission line and the qubit. Can we do this? Okay. To answer this, let us recall that we have a 1D system can achieve this kind of goal called the cavity. Okay. Now we have a cavity wall. Then due to the boundary condition of these two walls must be fulfilled, so we can have a standing wave structure inside the cavity. So this means that now if we put the atom coupled to this standing wave, we can just tuning or adjust the position of this qubit to have a different coupling strength. This means that now if we compute the natural line width of this atom as a function of the position, as you can see, it's truly the periodic function. It's proportional to the sin square function here. So this means that you can use this kind of concept to change or to adjust the coupling of the coupling strengths. Okay. So our idea is that how to combine the two concepts or two ideas, and this can be done by using the so-called terminated transmission line, and that is we have a transmission line with one end connected to a very large capacitor, so then we can have like a short circuit, something like that, and then in this sense, this terminated end can be treated as a mirror or behave like a mirror. Okay, so now if we have an input signal here, and then it will pass along this guide, and then when it hit this terminated end or hit the mirror, then it will reflect it, or it will reflect back, and then we can get the reflected signal. And this input and the reflected signal, they can interfere with each other to form a standing wave. So if we draw the field intensity as a function of position, as you can see, it's truly the standing wave structures. Okay. So suppose now we have a qubit coupled to this terminated transmission line, then we can just simply adjust the position of these atoms, to tune its coupling strength. Okay. So this kind of concept has been realized by Yao-Chun Ho's group. Okay, this is the experimental setup. They consider they have a transmission line here with this one end being terminated, can be behave a mirror, and they have a qubit here, and also they can fit in the input signal from this port, and then they can measure the reflected signal at the same port. Okay, so this cartoon shows you the model of this experimental setup, and here is the mirror. You can see the qubit is put in front of the mirror, and in reality they can apply the external flux to tune in the transition wavelengths of this qubit, and this means that they can effectively tune in the position of the qubits. So this they measure the line width or the line width of this qubit by tuning by change the effective position of the qubit. As you can see, the results agree with the theory prediction very well. So this means that we can use this kind of setup to probe the properties of vacuum by by changing the position of the qubits. So once we know that, we are asking a question to go a step further, like how about many particles? Okay, if what happens if we add more particle in such a system? Okay, and there is some of there's many particles effects, but now I'm just show you one of them. It's called the dipole interaction. So the simplest many particles system is composed of two qubits. So in here we consider the two qubit case. Okay, they are separate but distance r, and then as we know, these two qubits can be exchanged photons to each other, and they will build up a correlation between them. And this kind of correlation is called a dipole interaction. And this interaction will introduce two additional important quantity. They will affect the property of the two qubits. For example, if as shown in this blue curve, it's the mutual decay rate, and also this kind of effect will also introduce the other called the collective energy shift or collective length shift is represented by the red curve here. And as I mentioned, that this kind of system has a standing wave profile, so it must be a long range periodic behavior. Okay, and well, the best way to understand the effect or to see how these two quantity influence the these two qubits is to use the energy diagram here. So now we have two level atom here. We have 4 energy states. Okay, here EE stands for the 2 excitation states. GG stands for the ground state, and here the EG plus GE and the -1 is the single excitation state, which is called the symmetry state and the anti-symmetry state. If there is no such interaction, these two single excitation state is degenerate. Okay, and then this kind of effect will introduce shifted these two symmetry state by the amount of delta 1, 2, so the energy will be split, and also the photon transition rate between for these two patterns are modified by the Marshall decay rate here, and the emission rate enhanced patterns here we call it as a superradiance. And on the other hand, the weakened, the superradiance is called a subradiant. And well, this dipole-dipole interaction is also has been observed experimentally. And we work with the Professor Ho's group. They are perform the experiment. We are doing the theory part. This is our experimental setup. We have a transmission line, and we have two qubit, and here the qubit 2 is put in front of the mirror. We get two qubit system, and the corresponding model is like this. We have the mirror here, and we consider all the qubits are in front of mirror. Okay, and the black solid line stands for the resonance mode of this qubit, and the gray one stands for the other modes. Okay, so so we measure the reflection spectrum as here shown here. Here the solid line stands for the theory, and the circle dot is the measurement results. The first thing that I want to say is our theory agree with the experimental quite well, and also that here we observe we have a two splitting dips, and this splitting dips is just a direct measure of the collective length shift. So this means that we have observed the dipole interaction in this such a system. Okay, and also I want to say stress that this kind of a system is different from the optical cavity, because in cavity case, then the atom are always coupled to the a single mode. Okay, but in this kind of architecture, we can have a standing wave profile, and also we need to consider there's a continuum modes of the environments. So now we know we are considering the one system is the terminated transmission line. Okay, and then we are going to talk about I'm going to talk about our artificial atom. In our setup, we consider we use the artificial atom called the transmon. So in the following, I will introduce you the concept of transmon. So this figure shows you the typical circuit QED system. Okay, and in this kind of setup, as you can see, the comb-like architecture here is the transmon. Okay, and its physical property can be understood through the so-called circuit model. So you can use circuit model to simulate the behavior of this circuit system. Okay, and in this model here, the box here is the transmon. It's composed of a linear capacitor and here the nonlinear inductor. So it can be modeled as a LC circuit, but the L here the inductor must be the nonlinear one. So to see how this nonlinear inductor affect the transmon, is best way to understand that to using the energy spectrum. So as a comparison, we here to the left one is considered the traditional LC circuit. Means that the inductor now is linear and capacitor is linear. So if you go through the quantization process, then you can get the quantum harmonic oscillator like energy levels. I mean, you can get equal spacing energy level between neighboring levels. Then how about nonlinear one? If we go through the same quantization process, then this nonlinear effect will introduce an harmonicity alpha here, so we can have non-equal spacing energy levels. And experimentally, in our experiment in the working regime, here the harmonicity is much larger than the line width of this transmon. So in this sense, that we can neglect the higher levels except the lowest two. Moreover, as we know that the transmon is a charged qubit, so this means that it must influence, the energy must be influenced by the electric noise. So, but well designed, but in reality, you can well design this device, meaning you can have the change or tuning this Joseon energy, the ratio between Joseon energy and the charge energy. For example, if you have this kind of value here, we can have the you can have the flat energy levels here. So in this sense, that the transmon now is insensitive to the electric noise. So by well design the sample and by considering the a very large anharmonicity. Okay, then we can treat this charge qubit transmon as a two-level atom approximately, and its excited state and the ground state is labeled by the E and the G respectively. All right, so now we have our one system and we have our artificial atom. Let's go back to our story. So our starting question is like, can we efficiently load photon on such systems? To answer this, now we have a terminated transmission line coupled, with transmission line with this one end can be treated as an anti-norm mirror, and also coupled to transmission qubits. Okay, so we are trying to study how to efficiently load a single photon on such a qubit. And there's a method called the time reverse photon. I will show you the idea first. So suppose we have a two-level atom here, and the atom initially in the excited state, and then when it undergoes the spontaneous emission, the energy will be released from the qubit, and then you can observe the energy or Swiss photon from this left-hand side. Then, if you observe this, you can draw or you can compute the emission profile as a function of time, and it's exponential decay waveform. Everybody knows that this property of spontaneous emission. And the whole idea is that now, how about we reverse this kind of process? If we reverse this emission profile as our input signal, inducting with this transmission qubit, what happens? Okay, so now we consider we have exponential rising waveform as our input pulse, inducting transmission qubits, and we can calculate the corresponding output signal to see if this single photon can be absorbed or not. Okay, and again we tackle this problem with the Professor Ho's group. So this figure shows you some results. Here, the dot point here stands for the experimental results. Solid line stands for our theory, and the black line stands for we have this exponential rising input. Okay, and the red one stands for our output signal. Okay. So the first thing is that our theory agrees with the experimental very well. And besides that, we also compute or measure the loading efficiency of such signal or input pulse. So in some conditions, then we can have nearly 100% loading efficiency. So we have the ability to tackle of this kind of questions. So we are trying to go a step further by asking, how about many-body states? Can we prepare?
Sorry, can I ask a question? I
okay.
kind of get lost. What's the purpose of this experiment? Are you trying to design a total reflection or total absorption state, or what's the purpose? Can you remind me?
Well, I'm trying to study how to efficiently load the photon on the transmon. So this means that we are trying to study what kind of temporal profile of the input pulse can be totally absorbed by the transmon.
Okay, so the total absorption by designing the input shape of the pulse.
Yeah.
Okay, I see. Thank you.
Okay. Well, now we know we can have the 100% loading efficiency. Then the next step is to ask how to prepare the many-body states. Can we prepare it by using the same idea called the time reverse photon? And well, the answer has been answered in 2018 by Leo's group. So now I will show you the idea they proposed in their paper. So now suppose we have an atom here, and it is in the excited state. And then when it undergoes the spontaneous emission, we can compute or calculate or get its emission spectrum. And the crucial part is that they perform a time reversal operation on such emission spectrum. And then they treat this spectrum as an input one or input spectrum and feed in the original step And after the absorption process has been done, the atom will go to the excited state. It is guaranteed because this is due to the time reversal operations. Okay, and to apply this concept to our system, let's start with the emission part. So now we have a terminated transmission line coupled to a transmission qubit array here, and our system can be described by the Schrödinger equation. Well, because we are considering how to prepare a single excitation many-body states. This means that we can find ourselves in a single excitation inside state here. We include the atomic amplitude and also the photon degree of freedom is considered in our in this in this state. So now suppose our atom, this qubit in an arbitrary single excited state here, and then we let this system fully evolve. Then eventually this atom will emit a photon, and then we can calculate the corresponding emission spectrum here. And then to do the time reversal operation is easy. We just take a complete conjugate of this emission spectrum, treat it as input spectrum, and feed in our system. And after this absorption process has been done, then the atom will go back to the desired state. Okay. So now,
sorry, may I ask what's the requirement for this ansatz? I mean, does it require the gap between the energy level to be much larger than the energy, the photon absorption level? What's the assumption there for the ansatz?
You mean why we use this single section sector? Section sector? Yeah. The first thing is that we consider the input pulse is a single photon.
Yes.
Right. And also our Hamiltonian is energy conserving. So in that sense, so we can only consider the single excitation states because the other states are decoupled from this equation, from this Hamiltonian. Yeah.
I'm asking why other states are decoupled. Is that because you just emit? Because
you have only single excitation. You have only single excitation as your input, and your Hamiltonian is energy conserving. So you can only,
single photon assumption. Yeah. By your source. Yeah. Okay.
Yeah. We consider we have a single photon as our input.
Okay, I see.
Yeah, so this means that this system only has single excitations. So the evolution must confined in the single excitation subspace.
Okay, good.
Yeah, so that's why we only consider this single excitation inside state. Okay.
Okay, thank you.
All right, so now we have this kind of concept applied to our systems. So now we are trying to go a step further, asking some questions. For example, now here we notice that we are now trying to consider how to prepare a many-body states. And this, as we know, to the best of our knowledge, that this kind of many-body state is very hard to measure experimentally. So this means that now the measurements on such an atomic state is, still lacking. And we are asking like how to observe an arbitrary single-excited atomic state. Okay, we are trying to propose a method to solve this question, to answer these questions. And also we are trying to think about that. How about two distant qubits? The distance qubit here means that now the time for the photon travel between this qubit matters. This means that the time retardation now cannot be neglected. Okay, so we are trying to answer these two questions. So let's start with the first one, how to observe an arbitrary single-excited atomic state. To answer it, we need to consider a model composed of a terminated transmission line coupled to a transmission array here. And then we have time reverse photon as our input, okay? And then we can compute or calculate the corresponding output pulse in terms of output operators. So now the question, let me talk about creation specifically. Now we are asking, can we infer or get the atomic spectrum or no atomic states from this output pulse? Yeah, so the answer is yes, because we propose that we can use the Wigner function, the phase-space perspective, to help us to observe or to infer the atomic state from this output field, because it can be measured. It's very easy measured in experiment. So in the following, I will show you our ideas. Now, first, now we have output signal in terms of output operator. As you can see, by its definition, we have multi-modes. It's very hard to compute the corresponding Wigner function. So then we fill this output signal into a filter. The purpose of this filter is to fill out some a range of the frequency of interest. So what kind of filtering function that we are considering is like that. Now we are using the emission temporal profile of this qubit array as our filtering function. So this means that suppose the atomic state now is in this state is desired state. You want to measure this kind of state. When it undergoes spontaneous emission, you can record or you can compute the corresponding emission spectrum or the emission temporal profile, and we choose this profile as a filtering function like this. Then we can have the filtering function. After we apply this filtering function to fill some certain range of the output signals, we can change the multiple modes into the single modes. Here the capital operator capital A here stands for the single mode, and the single mode denotes the spontaneously emitted photon. This means that now we are now trying to study the spontaneous emitted photon from this transmon array. Okay, we are trying to use this emitted photon to study or to infer the atomic state of this transmon array. Now for two example.
For this filtering process, will it erase some information, or it preserve all the information?
Yeah, we erase some information. Yeah, because you just choose some range of frequency of interest, right?
Okay.
Yeah, because as you can see, the output signal is composed of continuous modes, and then we just choose some certain range of frequency that we are help us to infer the atomic states, something like that.
So you choose the profile to be the same as previous one. I mean, this blue shape emission temporal profile is the same as the one you used previously. I mean, to design the shape of the filter, it requires to be the same as the emission of its original one, right?
What do you mean the original one?
I mean, how do you design the shape of the blue curve?
Well, now suppose you have a desired state you want to prepare, something like that, suppose like that. And then when it undergoes spontaneous emission, you can recall where you can get the corresponding emission temporal profile, right?
Oh, okay. So that's its original.
For example, now if you have only single qubits in this array, so it must be the inside state. Then when it undergoes spontaneous emission, the temporal profile you get is the exponential decay, decaying function profile.
Okay.
Yeah.
So if it's not only single qubit, it's multiple qubit, and then
it's multiple qubits. We are consider the qubit array. It can has a larger of qubits. Yeah.
Then how do you know this shape? By assumption, you do not know, right? Or you know?
No, you know, because you want to prepare some. If there are some states you want to in general we don't know that, but now suppose we have something that we want to prepare, right?
Mm-hmm.
Something that we want to prepare, then you must have a target state here. Then you must know that. Okay.
Okay, I see.
I mean, Yeah, if there is some desired state you want to measure it, then you must know that what the desired state is, right?
Okay, okay. So
Yeah,
you know
so
your target.
yeah, I know my target states. Then according some by using some lensing calculations, then you can compute the corresponding emission temporal profile.
Okay.
Yeah. Okay.
Okay, okay. Thank you.
Okay, so now after this building process, then we are now starting the spontaneously emitted photon by this transmon, and we are trying to use this photon to help us to infer the atomic states. So let me show you some examples. Now, first, suppose now this input pulse is totally absorbed by this qubit array. This means that we can get the desired state. And then when you release this photon, we start this kind of emit photon, then we can get the single photon properties or behavior of the output field. Now, at other extreme case, like now, if this input pulse cannot be absorbed by the atoms, so this seems that this atom is always in the ground state. Okay, so it cannot emit photons. So there's no photon can be observed after the loading stage. So this means that the output force must in the vacuum states. So in reality, the situation must in between. Okay. So now once we know that, I can show some numerical results. So in here, we are considered to prepare the time decay states. Here we have 5 qubits with the distance r. We are trying to prepare this kind of states. At first, they were using the time reverse photon to compute time reverse photon as our input pulse. As you can see, in terms of the input photon flux as a function of time, the temporal waveform is very weird. And to see that if these qubits, this state can be prepared or not, naturally we can calculate the corresponding population. The population here is the desired state population here. As you can see, at the time at t equals to 0, this means that the loading stage has been done. Okay, so in that sense, we see that there is population reached to 100% efficiency. This means that we can use this time reversal photon to prepare an arbitrary state, okay, atomic states, many-body states. But our question is, how about the phase-space perspective to this state preparation? Then we calculate this emitted photon Wigner function that we find for this emitted photon. As you can see, it's like the single photon flux state. So they give us so this suggests that now if you can measure this kind of single photon Wigner function, then this means that you can prepare this time decay states. And also we are trying to consider a more realistic case because in experiment the pure dephasing process is always there. You cannot neglect it. So now I'm going to talk about consider this the effect of pure dephasing from the perspective of the phase space. And to see this, we introduce the fidelity as a function of the dephasing rate. Here, as comparison, we also draw the population of the desired state. As you can see, although these two curves not the same, they are not overlapping to each other, but the trend of these two V curve are similar or are the same. The trend is the same. So in this sense, we can say that our fidelity can reflect the fact that the state can be prepared, well prepared or not. Okay. So as we see that now this population of fidelity is decaying with increasing the dephasing rate. This means that now a desired state now cannot be well prepared. Okay, and then how about the Wigner function change as increasing this dephasing rate? So we calculate some cases. For example, the ideal case is I just shown in the last slide that we have. If you don't have any, if the pure dephasing process is neglected, we can get the single photon Wigner function. now we are trying to use our experimental parameter to compute the corresponding Wigner function, as you can see here. So this means this suggests that we can this state can be prepared by our experimental setup, and also we increasing the pure dephasing rate. As you can see, the change of this Wigner function must from the single photon Fock state to the vacuum the coherent state. So this kind of sign can help us to identify whether this data state can be prepared or not. Okay. So now let's go to the second question. Now suppose we come. How about two distant qubits? Can we use this kind of time reverse photon concept to prepare an entangled state between qubits? Okay, we are trying to answer this. So we are considering a model. Again, it's a terminated transmission line coupled to a two distant transform. Okay, in here they are separated by a distance r here, and also this r introduce a time delay tau defined by the r over vg. Here vg is the speed of light. So this physical meaning of this tau means that the time needed for a photon travel between this transform. For example, if you take time tau for a photon comes from the left transform to the right hand side. Okay. And also we have a time reverse photon as our input pulse. We are trying to they can interact. This pulse can interact with this two qubit system. Okay. So further thing that we are trying to study the dynamics of the two qubits. So by applying the string equation, we can get the dynamical equations of the two qubits. Okay, here the C1, C2 stands for the atomic amplitude for the qubit 1 and the qubit 2 respectively. And there is some finding for these two equations. The first one here, the C in part means that we have the input pulse interacting these two qubits, and also you can see this interaction is influenced by the time delay tau. So this means that you cannot the input pulse, now the pulse cannot interact with two qubits at the same time. It must have some time delay on this kind of interaction. Okay, and also here these two terms describes the dipole-dipole interaction. As you can see, there is some time delay here because you need some time because the dipole interaction is due to the exchange photon between pairs of qubits. So you need some time for photon to travel from qubit 1 to qubit 2. Yeah, so this kind of time delay will influence the dipole interaction, which will lead us to the non-Markovian dynamics. We will see this later. And also we find out that we always have this factor of 2 tau here. Then it can be understood from the image qubits model. Here, this image qubit is about the concept like the image charges from the electrodynamical theory. So this means that we can extend the terminated transmission line to open transmission 1. To fulfill this boundary condition here, we need to introduce two image qubits here. It's labeled by the index m here. So naturally, you can see if you this kind of model, that you can see that the factor of 2 tau comes from this image qubits. It's naturally a rise. Okay. So now we can show you some numerical results. So in the first, I will show you the non-Markovian dynamics of the qubits. So now we are initially we set up our system initially in the symmetry states here, and also this figure shows you the dynamics of the population of the qubits. As a comparison, we also draw the single qubit emission, exponential emission decay, and also the superradiant decay. Okay, and the first we observed that now the qubit 1 here, before the dipole interaction is established, then its behavior is quite like the single particle case. Okay, and now we are setting this time delay equal to 1. So in this point, the photon is reached emit from the qubit 2 is reached to the qubit 1 here. So the dipole interaction will be build up. So that's why we can have this kind of a very sharp changes, okay, or of these dynamics. And also, once this kind of induction has been built up, we observe that there is some regions, regions that the photon emission rate is larger than the decay superradiance. And also, we see that in some regions we can have a negative decay rate as a witness can be witnessed as a non-Markovian dynamics. And we also compute the second qubits. And the most important thing for this dynamics that is like that before the double potential now is established. Now you can see that the decay rate of this distant qubit now is smaller than the single particle due to the quantum feedback effect. So in that sense, we can say that now the super or subradiance is more like the local properties. It's no longer the global properties. Okay. So so in the end, I'm trying to. Yeah.
Sorry for interrupting. So what's the quantum feedback? Are you?
Quantum feedback means that, quantum feedback you can think is quite like the time delay effect, because this qubit 2, you put it in front of mirror, it's a very large distance, so you need some time to let the photon comes from this mirror and go back to influence yourself. So this kind of effect is called the quantum feedback effect. Yeah.
I'm just curious. It looks like a time delay effect. What was the quantum? Or you just name it as a quantum?
No. They call this kind of effect is quantum feedback, because you need some time to influence it yourself later.
Okay.
So it's called a feedback, and the quantum means that it's fancy word. Yeah.
Okay.
Yeah. So you're right. It's just time delay effect. Yeah.
Okay.
Okay. So in the end, I'm trying to show you to see if the entanglement between two nodes can be invented or not. Okay, so now we consider we are trying to prepare a symmetry state for these two qubits. So at the first, we have the input pulse in terms of photon flux with a time delay 1. As you can see, the shape is weird, and to see if the integral state can be prepared, then we calculate the corresponding population of this symmetry state here. And also, as you can see, when the after loading stage, the population reaches to 100%. This means that the desired state can be prepared with 100% efficiency. So this means that now we can use, in principle, this time reverse photon to prepare to entangle two nodes of qubits. Okay, two nodes. So now I'll conclude our work. In the first thing, that now if the pure dephasing process can be neglected, we can observe the single photon flux state, which will tells you that the desired ground state can prepare with very high efficiency. And also the second one is that now if the dephasing rate is increasing, then the Wigner function must change from the flux state to the coherent state. And the third one is that we derive the couple time delay dynamical equation, and some physical meaning of these equations can be understood from the image qubit model. And in the end, that we propose that, in the end, we know that we can apply the single-time reverse photon to prepare arbitrary state of two distant qubits, okay, with very high efficiency. So, well, that is all. Thank you very much.
Thank you, Kuan-Ting. Is there any question from the audience?
Sorry, I may want to ask, how do you know it's entangled? The two states are entangled. I kind of not get the point.
Well, this state in two qubit system, this is the most entangled state. Is the symmetry state? This entangled state. Yeah.
How do you know it's entangled? From the measurement or from the?
No, this state is entangled state already. We are trying to prepare an entangled state.
Oh, okay.
maybe you can calculate some concurrence to see if this is entangled. But I'm saying that this state is already the most entangled state for the two-qubit system.
Okay, so you are trying to you already know it's entangled, so you are trying to see its fidelity of the propagation, the unity efficiency, something like that.
Yeah.
Okay. And the other question is how do you know there is a image mirror from your slides, page 21st. I forgot of yeah. How do you know there is an image? I mean, will it reflected back from the left hand side, or how do you know it, why it makes a mirror there?
Okay, I see. Because we can expand this to tau like by using the pulse reflected by the qubit. You need the time to tau to interact with the qubit too. I know this kind of explain, but in our previous work, that if you consider trying to calculate the dipole interaction, you can have the additional time comes from it's different from the open transmission line, so they can be interpreted by using this kind of image qubit. So that's why we use our model to explain some quantities. Yeah, here.
Okay, I see. Sorry for another simple question for your just in the very beginning about the single qubit. You try to locate the position dependent of those gamma, the line width is corresponding to different coupling, and I'm just curious about the experimentally, do you prepare many different sample for those qubits at different position and you make many measurement, or how do you do this?
You know, experimentally, how do we change the position of this qubit, right?
Yeah.
Because we are considered you have a screw device, you have a transmit, so you can just tune in the position. You can just apply an external field, okay, to change the transition frequency or transition wavelength of this qubit, right? And then yeah. And this qubit is put in front of a mirror by distance L here. So you can only change this lambda, the transition wavelength. You can effectively change the position of the qubits. So it's called effective position. It's not the physical position.
So what you change is the wavelength of the input signal, and then effectively their position, the field is different.
Yeah. We just only change the transition wavelength, then they will give you the changing of the effective position of qubits.
Okay, thank you. Yeah, I'm good.
Hi, could you remind me again why you consider like one qubit in the transmission line, wave line, and later you consider like multi-qubit case? Is it better or is for different cases?
Well, in different cases, at the starting point, we need to deal with the simplest situation, right? So in the beginning, we are trying to study how to transfer the energy from photon to a single qubit, and then we are trying to consider can we go a step further by transfer this energy to prepare a desired single excitation many-body state.
But like, so this single photon contains like multiple qubit, or I mean, or is just only one qubit? Like previously, I thought it's like I have some information in this photon, and I want to like transmit to somewhere else, and then so I need to do this photon and transform to qubit. So I was yeah, I don't know whether like if it's one qubit information, then why I just need 1 qubit in the transmission waveguide, or
So what do you mean by 1 qubit information transfer to 1 qubit transmission line?
okay, like I look at the abstract from the your work, and so I just get some idea. I thought it's like it's so I mentioned it's like so I have some result I want to transmit from maybe one quantum computer to another one. So I use this photon to transmit the information. Or isn't that the case?
Yeah, you can say that. So we are consider, I mean, we are considering how this photon can be totally absorbed by the single qubit or the qubit arrays.
Okay.
This is our problem that we're trying to solve.
Okay.
The question that we're trying to answer, yeah. So this single photon can be absorbed by a single qubit, or it can be absorbed by a qubit arrays. I think there's two different cases. Is that your? Am I answering your question, or?
So if I mean, so if I have the same single photon, and I have many copies, then I just one I send to a transmission waveguide only with
No, in our consideration, we only have a single photon. We don't have any other photons. There's only one single photon.
Oh yes, I just want to emphasize is the input is the same, and if I have the same results to the single qubit in the transmission waveguide, and another one is multiple qubit transmission waveguide, and with the same input, then what's the difference between the two?
We have the same input. I mean, in the energy perspective, we have only single photon energy. But if in the viewpoint of the temporal shape of this single photon, they are totally different, because you need to efficiently absorb this photon. You need to do some photon shaping process. You can have as I mentioned, that if in single photon you need a time. You need an exponential rising temporal profile as your input pulse. But now, as I just showed you, in many cases, for time decay states, you have a very different temporal waveform. They are different shape.
Okay.
Yeah. Well, you may think they can contain different frequency component because they are the same. Yeah.
Okay, thank you.
And any other question from the audience? Okay, if no, I think it is about time. And thanks, Kuan-Ting, to give us this clear and insightful talk. Yeah. Thank you, Kuan-Ting.
Oh, thanks.
哎，学弟，谢谢你。
哦，不会啊，不会，不要这样，学长，来啊，对吧？所以你们现在都在办公室吗？还是你们现在也是分流？
我们现在大部分应该都居家。
哦，
对啊。
啊，要是到疫情比较缓和的时候，这样子吗？
其实我也不知道什么时候会，应该说公司的政策，防疫政策还不确定是怎么走。
OK，
因为其实现在好像也很难防，就是反正就是周遭都很多案例发生，所以对啊。
哦，对，确实是这个样子，对啊。
是啊，所以也不知道会不会之后干脆就不熟了。
应该吧，我也不晓得我算是我也都很少到办公室就是了，就是。
哦，所以你们现在都在台，就是哦，如果没有疫情，你们都在台大。
对啊，我们都要每天都去办公室啊。像我们在哪里做都一样，我们做理论嘛，但是还是去学校比较好。
是啊，就是还是有个办公的空间，大家可以讨论的空间这样子。对
啊，是没有错。
嗯，
对啊。
学弟想问你哦，虽然这个好像有点离题，就是现在这种就是传递 information 的，现在 mainstream 的方式是什么
mainstream 的方式哦，
对，
其实我也没有很了解这个 mainstream 的方式是什么，就是对啊，我们都才在刚开头而已啊，就是我觉得就是因为现在这系统就是做这相关的很少，所以对就先做再说这样。
哦。
所以他们实际上做到这，他们如果真的要做 network 嘛，我觉得应该不会，就只 demo 它可以做high efficiency 的 transfer 这样而已。
哦，因为那个好像蛮多人想要弄的，就是 ion trap 那边也有。
对啊，很多 platform 都会有，对啊。所以我们这里因为我们都跟实验合作嘛，所以
对，
这个那个 setup 不是就 superconducting 不是 superconducting 哦，这个还不算是蛮常见的，对不对？
对，就是因为我们阶段一段嘛，如果 superconducting 大部分都是 circuit， 就都是 QED，都是那个 cavity 或者是像 fiber 那种的就 open 的，这种一端截断的就等于你就封死一段了，不是吗？就只能当 receiver 吧，我在想。
什么意思？你是说之前说可能也是整段很长啊？
如果你要传递讯号，你要不是一定要可以从左边传到右边嘛？我们右边被我们截断了，一边被截断了。
哦。
所以这不能当成中间的，只能当成最后的啊，就是就是接收端那一种的吧？我在想，对啊。他就做一边可以输出，一边可以输入啊，这样两个是同一个的啊。
所以它整个还是在superconducting的架构下，是不是？
那需要你说什么？对不起，需要你说什么？
然后它整个还是实验跟那个superconducting的架构很像，只是一边封起来，还是我搞错？
对啊，我们现在考虑都是这样，一边封起来接到接地啊，或是接一个很大的电容啊，然后它就像个镜子一样啊，所以它就 standing wave 啊。
那这个是会比一般没有接起来还要好控制，或者说比较多性质可以讨论。
就是说你没有接起来的话，你没办法控它的位置就没有那么就觉得位置就不重要，因为它是 traveling wave 啊。那我们用这就是你可以多了可以 control 它的位置，然后增加不同的 coupling 的强度之外，重点是你在像我们刚才讲的那个什么 dipole point 选的一些效应都会比 open 的好很多，很明显很多啦。
我的直觉就是一边封起来，因为有 standing wave， 所以很多东西会比较准，比较好控制，是不是这样？
对啊，对，没错。而且重点是它跟 cavity 比起来的话，它是 multiple mode， 它 continuous mode 都要考虑进来才会对。就是它又没有那么 cavity， 可是它又多了很多可以操控的条件。对，它等于是模拟一个一维的 space， 然后有一个 atom couple 这个一维 space 这样子。
为什么会有 continuous mode？ 是因为它有持续 input 再进来？
没有啊 ，continuous mode 是这个vacuum 吧
？vacuum。
对啊。
哦。
就是它可以 supporting 的这个，就是你现在这个 device 这边，你可以去做一些什么，算一些什么，它能 support 的 mode 嘛，的模态嘛。啊，他们就是那个是 continuous mode 的，因为他们实验做过一个 two-qubit 的 case， 就一个摆在那 entangled 一个摆在 node 的时候，就是原本你一起 decouple 的效应都出来了，就是一定要考虑 dipole-dipole 的选出来，对，那就一定是要 continuous mode 才会有的效应，对。
我没有 get 到，就是为什么一般的没有 continuous mode，你这个有？
因为 cavity 的那个不是第二个 mode 跟第一个 mode 差很多，频率差很多嘛。所以它跟 atom couple 的就比较就只有一个 mode 一样。
等一下，你的 continuous mode 是指 couple 吗？还是指什么？
就 environment 的那个 mode， 就 electromagnetic 的 wave 那个 mode 的频率。
可是，一般的 case 不是也有吗？
可是，一般 case 你要 standing wave 不是只有 cavity 吗 ？cavity 不就只有一个 mode 而已嘛？因为第二个 mode 频率差太多了，就 decouple to 你的 atom 嘛。
cavity 是两边封，是不是？
对啊 ，cavity 是两边封，我们只封一边啊。
OK。所以你的那个 energy level 比较近，所以就会被 couple 起来。
对啊，所以很多 level 就会被 couple 起来这样，然后就会有一些就是 vacuum fluctuation 的效应，就会看得到啊。
了解。对
啊 ，cavity 是看不到的，就是除非你要 well design 的 cavity 才可以啊，因为它在 gigahertz 的 range 嘛，所以对啊。
你可以再秀一下 slide， 我刚刚第10页好像还是有一个问题，我忘记。
等我一下啊，等一下啊。
好。
第10页是不是？第10页在哪里？
记错的话。
这个。
还是11页 ，OK。
这个。
我想问你，那个不同的 charge， 你的横轴那个不同 charge 是在讲什
么？你可以想成这就是你不要想成是一个 electric noise， 就这 NG 是你不要的量，就是你一定会你跟别人 couple 在一起，这个不是你不要，你可以想成它是一个 electric noise 的概念。对，所以当你今天如果你这个 ratio 设计的不好的时候，你的 energy level 是很容易被影响，它就不是平的。它就是有一个 charge 少一个 charge， 然后它就会多，它就会变成一个震荡这样子。可当你 well design， 它就是平的，这样对做理论做深度比较好，不然你就要给一个 time dependent 的 frequency， 而且是 random。
所以那个 charging 是指那个 qubit 上面有 charge 不同电量吗？
因为它有一个 gate， 它是一个 couple， 好像是一些这种寄生的，你跟别人 couple 本来是只有这样的，可是这个效应会进来影响到你，这就不是你要的这样。
那是寄生过来的。
对，就是因为你跟这些东西 couple 在一起，它有可能会有些电容效应，有可能有些 charging， 然后这 charging 本来就是很 random 的，所以你可能就会有一些这种很奇怪的这种震荡。所以当你 well design 你的 sample 应该就会比较好。
我有点好奇，那个 cavity 怎么吸引电子过来？对
cavity 怎么吸引电子？
你不是在 cavity 上面做吗？或者不是 cavity，
它是 EM wave， 它 EM wave 它还是能穿过去吧？它就看起来，因为它是 EM wave 啊，所以传输线不就是会有一些阻抗的效应嘛？那它还是会传出去啊。
OK， 还是电量还是可以传出去。
对啊，它是
那你上面怎么放 qubit？ 你的 qubit 是真正有 superand，
就 amount 上去啊，它就是一个平板，它是 plain 的啊，然后你就是对啊，
然后你封一边，然后变半开放的 cavity， 然后还是一样把那个 qubit 放上去这样。
对啊，它就是 mount 在那个板子上面的一个板子上的。
因为 cavity 我都会想成像一个枪这样，其实是在平板上。
它是一个平面的，它是一个平面。你看它这个就是完整的平面啊，就是它是平面的。
OK。
对啊，所以它像这个，它就坐在这里啊，这个它就截断了。
OK。
这段它截断，然后就是这个，然后 qubit 就放在这里。
OK。
对啊，那它之所以会绕，是因为这样子可以比较省空间啊。如果你做直的很长就是 sample 就很长。
OK， 你放是真的有放一个那个 squat 上面是不是？就是一个。
对啊，他们真的做上去，这个是他们实验的图啊。
OK， 了解。
对啊，这个都是实验的图，只是有一些我没有他们很多实验的 detail 的图，就是确实是真的，他们是可以看到这些东西的，他们真的是放上去的。
了解。 不错啊，这些蛮有趣的。你这个刚开创领域，这个以后就变大师了，这样很好。
我也没有，只是台湾做这理论的很少而已啦，因为国外很多人做这个啊。
真的、国外很多人做。OK。
对，台湾做这个 superconducting 相关理论的，我觉得好像蛮少的。
我知道，可是我一说这个继续开创下去，还有很多可以玩的吗？还是就是
现在他们都就他们这领域我也不晓得怎么样，就好像就是因为他们这个 setup 比较特别一点，所以他们如果看到有些东西有人量了，然后在他 setup 再量一次，他也可以发一篇。
哦 ，OK， 听起来不错，很赞。
对，反正我们项目有个人实验嘛，然后有一些东西像 proposal 一些东西，他们如果能量，他们也会量，只是我们下大部分都跟着实验一起看他们想看什么，然后我们想看什么 proposal 互相一下这样。
了解，不错。
对啊，希望你们这边都还好吧？
就大家都居家是还好，对，我是还好啦，我不知道其他人，对，应该是，我想应该也还好。
哦 ，OK。
OK， 我见你是不是又开始录了？
等一下哦，我可能只是还没停止吧。
那你可能之后要